So this week, again, we'll be looking at our last two sections in the algebra portion of the class. And they're on what we call sequences and series. So we're going to start with sequences today, which is basically it's just a list of numbers, and you're trying to find a pattern in those numbers. So if you've done that before, you might have heard of a couple different kinds of sequences. We're going to talk about arithmetic or arithmetic sequences, and we're also going to talk about geometric sequences. And then tomorrow and Wednesday, we're going to look at what's called a series, which is when you add up all the numbers in a sequence, right? And you try to get the answer. Obviously, if the sequence is small, you can just add it up by hand. But if the sequence is big, how can we add up all the numbers in a quick way? Right? And that's what we'll look at tomorrow and Wednesday. So in order for something to be a sequence, there does have to be a pattern to it. Right? We're not looking at like sequences of random numbers. We're looking at sequences of numbers where you can predict the next number based on a pattern. Right? So there's an order to the numbers. Generally, sequences are named with a single letter, and it's lowercase. So let's say that those numbers represent sequence B. When you put a little number next to it, that indicates the position. So B sub 1 would mean the first number in sequence B. B sub 2 is the second number. B sub 8 would be the eighth number. So that's the notation for what particular term you want to know. If you're looking for a specific term and you don't know its position, you can just say B sub n, where n represents whatever position. It could be the hundredth position, thousandth position. We don't know the position. Anytime you see a dot, dot, dot in a sequence, that means that there's a lot of other terms we're not writing down and we're skipping over, but they're there. Okay, so in order for a sequence to be unique, then there has to be some kind of rule or formula to find the terms. Right? And there's a couple different ways we can find terms in a sequence. One is by looking at the one that comes before it and trying to figure out a pattern. And then there's another way which doesn't involve looking at anything that comes before it. The problem with looking before to find something is, let's say you're looking for like the 500th term. Even if you can figure out a pattern, to do that pattern hundreds of times to get all the way to the 500th one, that's going to take a long time. So it would be better if we could somehow figure out a quick way to figure out the 500th term without having to figure out every single term before it. Right? If you had a sequence like this one, and you wanted to figure out the 10th term, that's not bad. You already have the first 4. You only have to do 6 more. Right? But in general, the best way to be able to find a term in a sequence is to find that term directly without having to find every single one before it, because that takes a long time. All right, so let's look at this one. And let's see if we can come up, without me really explaining anything yet about how to do it, a pattern or a formula. Okay, so a couple things. First of all, there's a dot, dot, dot at the end. What that means is this sequence goes on forever. Okay? Some sequences go on forever. Some sequences stop. All right? When you see a dot, dot, dot at the end, it goes on forever. All right. Now, does anybody see the pattern? I'll just label these in that first 4 numbers. You generally have at least 3 or 4 numbers so you can see a pattern. If you only have like 2 numbers, that's not enough. Right? You really need 3 or 4. Yeah.
You're adding 3 at the top.
You're adding. What are you adding 3 to?
The sequence.
Can you be more specific? Like, let's say you want to find the 3rd term. Just use that as an example. How would you calculate the 3rd term?
Add 3 from the term before.
Add 3 to the term before. What's the term before the 3rd term in general?
A2.
A2. Yeah. So the 3rd term is the 2nd term plus 3. But if you didn't know the 2nd term, that would be a problem. Then you'd have to figure that one out. What's the formula for the 2nd term? It's the term before it plus 3. Right? So now let's see if we can do it this way. That's what I'm going to put over here. What do you think the formula for the nth term is? It follows the same pattern as those 2 formulas. Yeah?
A to the n minus 1 plus 3.
Yep. A sub n minus 1. So that means when you put a minus 1 on it, that means before. So it's the term before that one plus 3. So that is one way that you could come up with a formula. The problem with that is if I said to you, what is the 900th term? Well, the formula for the 900th term would be what? The 899th term plus 3. Okay, what's the 899th term? Oh, we don't know. All right, so then what's the formula for the 899th term? And you have to keep doing that. You have to work your way all the way back to the beginning. Right? That takes a long time. So even though that's correct, it's not the best formula to come up with. Here's a different version. Does anybody see, instead of looking at the term that comes before it, look at the position of the term. First position, 2nd, 3rd, 4th. Does anybody see something you can do to the position number to get the term number? So something you can do to 3 to turn it into 8. Something you can do to 2 to turn it into a 5. Yep.
You can multiply by 3 and then minus 1.
Multiply it by 3 and then minus 1. Yep. If you multiply 2 times 3, you get 6. 6 minus 1 is 5. If you multiply 4 times 3, you get 12. 12 minus 1 gives you 11. So now, if I want to find the 900th term, that's easy. The pattern is take the position you want, which is 900, times it by 3, and then minus 1. So 900 times 3 is 2,700. Take away 1, 2,699. So this second formula is a much better one. It gives you a way to predict a term based not on the one that comes before it, but based on the position that you're looking for. So position is better. And there's a name for each one of those, which we'll talk about. All right, so there's two different kinds of sequences. Okay, the last one I mentioned, it ended in a dot, dot, dot. Okay, when it ends in a dot, 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 that's called an infinite sequence. The idea of an infinite sequence is it goes on forever. Now, let's look back at this formula for a second. When I say the domain, I'm talking about the domain of that formula. Why wouldn't it make sense, since the domain is positive integers, why wouldn't it make sense here to plug in like 1.7? I mean, mathematically, you can do that. 3 times 1.7, take away 1. But how come when you're talking about a sequence, a decimal wouldn't make sense for n? Well, what did we say n represents there? It represents the position. So why can't you have a 1.7th position?
Because you'd be going between positions.
Yeah, you'd be between positions. You can't do that, right? You can be at the first position, you can be at the second position in the sequence, but there's nothing between the first position and the second position. There's no number in between there. So that's why when you're using these formulas and you're trying to predict a term, you have to use an integer. Also, why wouldn't a negative number make sense? For n. Why do you think a negative wouldn't make sense?
You can't have a negative position?
Yeah, you can't have a negative position. The first spot in a sequence is called the first position. There's no negative positions, there's no zero positions, there's no decimal positions. There's only positive integer positions, starting at 1 and going up. So in an infinite sequence, the first position is 1, and there's an infinite number of positions. It never stops. That's different than a finite sequence. Okay, a finite sequence starts at 1, and it stops somewhere. So the highest numbered position that you have is fixed. Okay, it can be in the millions, it can be in the billions, but if it stops somewhere, it's finite. Right? Even if your sequence has 20 billion numbers in it, that's not infinite. It's a lot of numbers, but it still stops. Okay, so any question on the difference between an infinite and a finite sequence? Infinite goes on forever, and you can plug in any positive integer. Finite stops somewhere, and you can only plug in up to a certain spot. Like if this was our sequence right here, and that was the whole thing, what's the highest position in that sequence? 4. 4. So you would not be able to plug in a number higher than a 4 to find something in the sequence, because the sequence doesn't exist after 4. It stops. All right, let's try this one. So this is just practicing listing out the terms in a sequence. So I give you a formula, and we're going to plug in numbers to find the result. Okay, so they want to know the first term. What would you plug in for n to find the first term? 1, yeah. So if we plug in 1, what's 1 squared?
1.
And what's 1 take away 1?
0.
0. And remember, we're plugging in 1. What's 0 divided by 1?
0.
0. That's the first term in the sequence. Okay. What would you plug in for n to find the second term?
2.
2. What's 2 to the second power?
4.
4 take away 1? 3. And what number did we plug in?
2.
2. There you go. That's the second term. Let's do the third term. 3 squared is
9.
minus 1.
8.
8. And we plugged in what number?
3.
3. And now, because the formula relies on position and not the term that comes before it, we can jump right to the 15th. We don't have to find the 4th through the 14th to get to the 15th. We can skip it. If this formula had something like this in it, then that would mean it depends on the term before it. Then we'd have to find a lot more. Okay, but let's jump to 15. What's 15 squared?
225.
Minus 1?
221.
224 divided by 15.
Is 225.
Yes, it is. Minus 1.
Oh,
Yep.
sorry.
And sometimes, if you change it to a decimal, you might start to notice what's happening. Okay, the first one is 0. Okay. You don't have to write the decimal part down. What we have in green, those are correct. That's what they want. We have 0. The next one is 1.5. The next one is 8/3. It's about 2.6 repeating. And then the 15th one is 224 divided by 15. Here's where I think you'll start to see the pattern. 14.93 repeating. That was the first position, second position, third position, 15th position. As you go further and further down in this sequence, how does this number start to compare to that number?
It's wait a second. It's getting close. It's like an asymptote.
It's an asymptote. It's getting very close to it. And that's because the only reason it doesn't reach it exactly is because the top is always going to be off by 1. All right? So the further down you go, the closer that this number is going to get to that number. So if you go all the way down to, let's say the 30th term, 30 squared is 900 minus 1 is 899. Look at 899 divided by 30. 29.97, very close to 30. All right, any questions on how we found those terms? Okay. Let's try this one. Okay, same directions. List the first 3 terms and the nth term. All right, what are we going to plug in to find the first term? 1. What's negative 1 to the first power?
Negative 1.
What's 2 to the first power?
2.
Negative 1 times 2?
Negative 2.
Negative 2. There's your first term. Okay. Second term. What's negative 1 squared?
Negative.
What is it?
Negative. Oh, what's 1?
1. And 2 squared?
4.
And my term?
4.
4. Okay. Third term. What's negative 1 cubed?
Negative.
Negative 1.
Negative 1. And what's 2 cubed?
8.
8. And my term itself is going to be?
Negative 8.
Negative 8. And the 15th term. What's negative 1 to the 15th power?
Negative 1.
Negative 1. Okay, 2 to the 15th power. And just do that out. 32,768. And my answer?
Negative 32,768.
Negative 32,768. So notice the pattern here. It's doubling each time. But what else is it doing? Yeah.
It's swapping, it's like negative sign.
Yep, it's alternating positive and negative. So anytime you have a negative 1 to a power, that's going to, and it's multiplying, it's going to cause it to go from positive to negative every other term. Yep. Okay, any questions on that one? All right. So those 2 kinds of formulas that I just showed you, this one and this one, are what we call explicit formulas. Explicit means you can find any term that you want directly without finding any in the middle. You can jump from 3rd to 15th. You can jump all the way to the 4,000th term. Okay, explicit formulas are generally, those are the best kind of formulas that you can have. The other kind of formula is called recursive. Recursive is generally easier for you to figure out, right? That's like when you look at a pattern and you say, oh, you're just adding 3 each time. Yes, you are adding 3 each time. And that's easier to see. But if you look at the pattern that way, and I ask you to find the 4,376th term, well, you're only at the 4th one. You're going to have to add 3 4,000 something more times before you get to the one I want. Okay, so recursive is not the best formula to use. The way a recursive formula works is I give you the first couple. Generally, it'll be at least 3 or 4. And then the term that you want to find is figured out by looking at the one that came before it. Okay, not the best way to write a formula. Okay, so in a recursive formula, the term that you want to find is calculated by looking at the one that comes before it. If you don't know the one that comes before it, you need to figure that one out. And then if you don't know that one, then you need to go back another one and figure that one out. And you have to work your way all the way back to the beginning just to get one term that you want. Just because it's not as great of a formula, it doesn't mean I won't ask you for it. I might still ask you, find a recursive formula for the following. But I'm definitely going to ask you to find explicit formulas. Let's look at this one. Looking at the formula that I give you right here, based on the definition above, is that one explicit or recursive?
Recursive.
That is recursive. If you had to explain this to somebody in like 2nd grade, they wouldn't understand that notation. What is this formula basically telling you to do? To get the term that you want, do that. But can somebody tell me what that is? Yep.
You have to grab the term 4 and add it 3.
Right. If you want to know a term, take the one before the one you want and add 3. That's what that means. That is recursive. And because it's recursive, I have to give you a starting point. Okay? If you don't have a starting point, then you don't have anything to build off of. So here's your starting point. The first term is 2. How do we know that? Given. It's what I give you. So based on our definition, how would you find the second term? I don't want to know what the second term is. I just want to know the formula to find it.
And you add 3 to the first term.
Add 3 to the first term. All right? And now, let's look at what's the formula for the third term?
Add 3 to the second term.
Add 3 to the second term. So now, let's figure out the third term using this pattern. Okay, second term, plus 3. Do we know the second term?
Not yet.
No, work our way back then. Second term, first term plus 3. Do we know the first term?
Yeah.
Yes, because that was given. Okay, now we got the second term. So now we can get the third term. It's the second term. Plus 3. Yeah, 8. Sorry. So a couple of problems with that. One, if you make one mistake, it messes everything up. Especially if you have to add 3 hundreds of times. And even if you don't make any mistakes, it's still going to take a long time. Okay. Questions on that? All right, so this example says determine the first 4 terms and the 8th term. Is this one explicit or recursive? Recursive, all right? So that means if they want the 8th term, we need the 7th, the 6th, 5th. We got to go all the way back. All right, so what I've done is I made a chart where I have the position, and then I'll fill in the term. Okay, let's start with the first position. What term is in position number 1? 2. How do you know that?
It's given.
It's given. All right. Now, what does that, in English, simple words, what does this mean to do?
Add 4 to the term before.
Yep, add 4 to the term before it. So, second term, we're going to do a plus 4, and that'll give me 6. Third term,
10,
10. And fourth term,
14,
14. Now, I can't just jump to the 8th term. I have to keep going to get there. All right. So what's the 5th term? 18?
22, 26, 30.
Okay. So the answers that they want are right there and there. Okay. Any questions on that? Okay, so now we're going to see if we can take a formula that is given to us recursive, work out the first few terms, and then see if we can convert it to explicit. Okay. So first of all, what makes that formula recursive besides I tell you up above it's recursive?
A minus 1.
Right, a sub n minus 1. That's depending on something before to get the current one. Okay, so first term is 3. What's going to be my second term? It's going to be 8. My third term? 13. And let's do one more. Fourth term?
18.
18. So now, let's see if we can figure out a way to do something to the position number to get the term number. So I'll put it in a box. Term, position. So we got 1, 2, 3, 4, 3, 8, 13, 18. So you're trying to figure out something you can do to that to change it into that. Yep. Yep.
Can multiply the position by 5 and subtract 2.
Yep, that's exactly it. So it's multiply the position times 5 and then minus 2. 3 times 5 is 15. Take away 2 is 13. 4 times 5 is 20. Take away 2 is 18. 2 times 5 is 10. Take away 2 is 8. Now, how did you figure that out? Did you use a formula? How did you figure out it was times 5 and then minus 2?
I don't know.
You just kind of
It
looked at
just-
it?
Yeah, it just kind of came to me.
Yeah. So some of them, if it's just times a number and then add or subtract something, we can usually figure that out, right? First thing I might try is, okay, maybe it's just times 4. 2 times 4 is 8. 3 times 4 is 12. No, that didn't work. All right. So if it's just times something and then add or subtract, we can usually get it. But if the formula was something like, take the number, square it, times it by 3, minus 4 times the number, and then add 7. That you're not going to be able to guess. There's just too many steps in there.
Probably something.
So we generally are going to stick with sequences that are times something, plus or minus something. And if the pattern is adding the same number over and over, whatever number you're adding over and over, that number ends up right there. All right, so that kind of gives you a hint. All right, so if you're adding 6 over and over and over, the pattern is going to be 6 times something, and then it could have a plus or minus at the end. Okay, I'm going to show you a way you can figure this formula out if it doesn't just come to you in a little bit. All right, a very systematic method. Follow this step, and this step, and you'll end up with that answer automatic. Okay. All right, let's look at this sequence. So this sequence is called the Fibonacci sequence. It's probably the most famous recursive sequence that there is. And what do you notice about this recursive sequence? It's recursive, it's a little different than the other ones we've looked at. Yep.
Does it result in one every time?
No, we don't get a 1 every time, but look at how it's being calculated. What do you notice is different in the calculation of this recursive sequence compared to other ones? Yep.
I'm taking the term before the term you want and adding to the second term before the actual term.
Right, this one depends not only on the previous term, but on the term before that. So this is a sequence that depends on the 2 previous terms. Because it depends on 2 previous terms, I need to start you off with the first 2. So let's see if we can figure out the formula for the third term. So if that's a 3, what do you think would be over here for the calculation for the third term?
A3 minus 1 plus A times 2.
So ultimately that would be a sub
So
2
2 plus A sub 1.
plus a sub 1. So the third term is the second term plus the first term. Well, what's the second term plus the first term? 2. All right, let's see if we can get a formula for the fourth term. What would be the formula for the fourth term?
A3 plus A1.
A sub 3 plus what?
A sub 2.
A sub 2. So the fourth term is the third term plus the second term, which in this case would be 3. All right, let's do one more writing the formula. What would be the formula for the A sub 5?
A sub 4 plus A sub 3.
A sub 4 plus A sub 3. So you're just adding the 2 terms before to get the one you want. What's the fourth term plus the third term? 5. Now it's just a matter of how high do they want us to go. The first 6? All right, we need one more. What's the next term? 8. Yep. Okay, so that is the Fibonacci sequence. Now, the downside to recursive, if I said to you, what's the 200th term in the Fibonacci sequence? You could add 5 and 8, and then you get the next number, and then you got to keep going. It's going to take a while. You can convert the Fibonacci sequence to explicit, but that's actually quite a bit harder than what we did here. So we don't talk about that in this class. It is doable, but it's not that easy. All right. So any questions on what we got there? Okay. So the last 2 things we're going to look at are very special kinds of sequences. You could also call a sequence a progression. Progression of numbers, sequence of numbers, same thing. You can also pronounce this different ways. I say arithmetic. You can also say arithmetic. I usually say arithmetic when I'm doing like 4 times 2. That's arithmetic. But I guess people say it different ways. So, in an arithmetic sequence, the idea is that to get from one term to the next, you are adding, or it could be subtracting if you're adding a negative, but you are adding a number each time, or subtracting. Okay, that's an arithmetic sequence. When the pattern is adding or subtracting each time. The number that you add or subtract to get from one term to the next is called the common difference. So why do they call it a difference if you are adding each time? Well, let's look at an example. Let's take 2. What do I want to use? 5, 8, 11, 14. What is the pattern there each time? Adding 3. So 3 is what you call the common difference in that sequence. The reason it's called the common difference, what's 14 minus 11?
3.
3. What's 11 minus 8? 3. 8 minus 5? 5 minus 2 is 3. So if you take any term in the sequence and subtract the one immediately before it, that's how you find the common difference. Take any term you want and subtract the one immediately before it. If that comes out the same every single time, then you have an arithmetic sequence. If it comes out different, even just one time, then your sequence is not arithmetic. So no matter what term you take, the difference has to be 3 in this problem. It doesn't have to be 3 in every problem. Right? It could be 5, it could be 10, right? But it's got to be the same every time. This is the formula for converting a recursive into explicit if you have trouble just seeing the pattern. Okay, this is how you do it. Remember, n is a positive integer. Okay, there's no such thing as negative positions, 0 positions, or decimal positions. To convert something from recursive to explicit, it requires you to know 2 things. What is the very first term in your sequence? And what is the common difference? What is it that you are adding each time to get from one number to the next? So we already did this once. And we were able to do it because somebody just saw the answer. It just came to them. So now, let's go back to that problem, try this, and see if this works as a more systematic way of doing it, if the answer just doesn't kind of pop out at you. So a sub 1 plus n minus 1 times d. Okay, was it this one? Yep. And the 2 things that you're going to fill in for are the first term and the common difference. Don't fill in for anything else. Okay, so we already know the answer. Let's see if this formula gives us the same thing. What was the first term? Yeah, we got it in that chart right there. What is it? 3. And what was the common difference? What did we add each time to get from one term to the next? 5. Okay. Now, does that look exactly like that?
No.
No, but let's do it out and see what happens. First thing we need to do is distribute. What's 5 times n? 5n, and 5 times negative 1? Okay, and now does that look exactly like that? No. But we have like terms we can combine. What's 3 take away 5? Negative 2. So this formula gives you a way to automatically convert an arithmetic sequence to something explicit. You just need to know the first term and what you add each time. And yeah, you do need to do that out. Okay. Any question on that? Let's try it on one we don't know the answer for. Okay, so it says find an explicit formula. Well, if that's all I gave you, why wouldn't you be able to do that problem? That's impossible.
You don't have the first.
Yeah, you don't have a starting point. I got to give you something to start with. Okay, so find an explicit formula for that. Okay, so off to the side, we're going to write down the formula we need to use. First of all, how do you know that this is going to be an arithmetic sequence? Right, it's a plus 3. To get the next term, you're adding 3 to the one that came before it. Okay, so let's put down the formula and then we'll fill it in. What's the formula that you don't have to fill anything in? just the formula from the previous page. A1
Plus parentheses and parentheses, close parentheses.
times D. Okay. Now we need A1 and we need D. Okay. What is the first term in this sequence?
4.
4. So we're going to fill in a 4. And what is it that you're adding each time to get from one to the next?
3.
3. So it's going to be 4 plus n minus 1 times 3. And if we do this out, what's 3 times n? 3n. What's 3 times negative 1?
Negative 3.
Minus 3, and we have a plus 4.
Plus.
Okay, so that should be our formula. The way we can check it is let's use this to write down a few terms and check it against that. First term is 4, and if you add 3, what do you get?
7.
One more?
10.
10. First term, second term, third term. All right, let's plug in 3 and see if we get 10. What's 3 times 3?
9.
Plus 1? 10. Let's check. Plug in 2, do we get 7? What's 3 times 2?
6.
Plus 1?
7.
Perfect. So now, if you wanted to know the 30th term, way down there, should be pretty easy. What's 3 times 30?
90.
Plus 1?
91.
There you go. They didn't ask us to find the 30th term, but I'm just trying to show you, once you get the formula, how easy it would be. And if you asked me for the 91st term or the 91,000th term, I could do either one just as quick. All right, any question on that one? Okay. All right, so now it says the first 2 terms of the arithmetic sequence are given. We're going to find the 5th term, and you know what? Actually, just to make that a little bit more interesting, let's find the 50th term. 5th term would be easy. All you'd have to do is do the pattern. You already got first 2. Just do the pattern 3 more times, and you're at the 5th term. 50th term, I don't want to do the pattern 40-something more times. All right, so let's see if we can come up with a formula. Okay, so we'll fill that in. What's my first term?
And negative 8.
Negative 8. And this time, you got to figure out what are you adding to get from negative 2 to negative 6.
6.
Yeah. If it's an arithmetic sequence, the pattern is going to be addition. Okay, you might say, well, it could be times 1/4. Not if it's arithmetic. No. If it's arithmetic, it has to be adding or subtracting. And it is a plus 6. So what does that mean my D is going to be?
6.
6. Alright. So now 6 times n gives me 6n. And what about, Ricky, what's 6 times negative 1? Negative 6. What's negative 6 plus negative 8? Negative 14. Okay, there's your pattern. 6n minus 14. So now, the 50th term, 6 times 50 minus 14. What's 6 times 50? 300. And what's 300 minus 14? 286. And again, 50th term or 5,000th term, doesn't make a difference. With that formula, it's just as easy. Any question on that? Let's look at this one. Find a formula for the arithmetic sequence. What are we missing this time that we really need to figure out? Yeah, this is going to be the key right here. We have to figure that out. But we do have a couple terms. And we know the pattern is adding or subtracting. So look at the difference between 13 and 3. That's a span of how many numbers?
5.
Well,
10.
what's the range between 13 and 3?
10.
10. And how many jumps do you have to get to 3?
5.
You have to get from 13 to 3. So you have to cover 10 numbers, and you have 5 jumps to do it in. That means each jump would have to be worth how much? 2. Down 2. Right? So 11, 9, 7, 5. You get a span of 10 numbers, that's the gap, and you have 5 jumps to make that gap. So each jump is 2. So now, work your way backwards. What's the second one? And the first one?
7.
There we go. So now our pattern is the first term plus n minus 1. What's the common difference here? Negative 2. It is important you write negative 2. That's negative 2n. What's negative 2 times negative 1? 2 plus 17. There you go. And that's your formula. Okay, this is a very different kind of math than we've been doing, but some people like it better, some people don't. It's different. Okay. Any question on that? All right, so that's arithmetic. The last type of pattern we're going to look at is geometric. Arithmetic is when you add or subtract. What do you think the pattern for, well, you want to think of it as adding, because it's what you add each time to get from one term to the next. What operation do you think geometric is going to be?
Multiplication.
It's going to be multiplication. Yep. So in this type of pattern, to get a term, you multiply the previous term by a number. So if you want to know a certain term, take the one that comes before it and multiply it by a value. For a problem, that value is fixed. Okay, they'll tell you what that is. Now, D stood for common difference. Anybody have a guess what R stands for? Well, let's look at this. Let's take 2, 6, 18, 54.
The number you're multiplying.
So it is going to be the number we're multiplying by, which in this case is what?
3.
3. How could you calculate, if you're not sure, like somebody just doesn't see it, what could you do here to calculate that it's 3? Similar to how we calculated the common difference. Yep.
Like a sub n divided by a sub n minus 1.
Right. If you take any term and you divide by the one immediately before it, it will tell you what you are multiplying by. 18 divided by 6 is 3. What's 6 divided by 2? 3. Yeah. So if you take any term and divide by the one immediately before it, that's how you can figure out what you're multiplying by if you can't get it. So because the calculation involves division, does that give anybody a hint what the R stands for? Yeah? Good guess. All rates usually have division in them. But it begins with those first 2 letters. Same first 2 letters as rate. Actually, same first 3 letters. Ratio. Yeah. It's called the common ratio. So to calculate what you multiply by each time, take any term and divide by the one immediately before it. And I think somebody actually explained it just like this. Take a term, divide by the one that comes before it, and that's how you figure out R. I mean, usually you can see what R is, you know, unless the numbers are really, really big. But that's how you figure it out. All right, so now what we want is some way that we could do something to a 3 and turn it into an 18. Something we could do to 4 to turn it into 54. And that's what this formula is. So this is how you convert a sequence that's geometric into a formula. Okay, it relies on two things, just like before. The first term and the common ratio. All right, so let's try it with the one up above. What's the first term in that sequence?
2.
So we get 2 times. What's R? What are you multiplying by each time? 3. That should be the pattern for those numbers. Let's try it with the third term. If we plug in a 3, we should get 18. What's 3 minus 1? 2. What's 3 to the second power? 9. And what's 9 times 2?
18.
Perfect. Let's try it. Let's try plugging in a 2 and see if we get 6. What's 2 minus 1? 1. What's 3 to the first?
3.
And 3 times 2?
6.
6. Perfect. So now if you wanted to know the 10th term, just plug in 10. 10 minus 1 is 9, and then use your calculator. 3 to the 9th power times 2. So that's how you can figure out an explicit formula for a geometric sequence. All right, let's finish up with that one. So find an explicit formula, and they're telling you it's geometric. If you didn't know it was geometric, you couldn't tell by looking at those two numbers. I could say here, maybe the pattern is just adding something each time. But I know it's not, because they say geometric. Okay. What are you multiplying by each time to get from one term to the next? Negative 2. And if you're not sure, divide 12 by negative 6 and it will tell you. So it's times negative 2. Just put an X for times. So now you've got to think of something you could put here. So when you multiply by negative 2, you get negative 6. 3. Yeah, if you want to work your way backwards, just divide by negative 2. And that'll give you the one before it. All right, so now we know the first term, and we know what we're multiplying by each time. Okay, what was the pattern before we fill anything in?
First term times the ratio.
First term times the ratio.
The next one is the sum minus 1.
And minus 1. Okay, what's our first term here? 3. What's our common ratio? Negative 2. Do not multiply 3 and negative 2. You can't do that. Just leave it like that. Okay, let's check the formula. Let's plug in 3 and see if we get 12. Then I'll plug in 2 and see if we get negative 6. So if we plug in 3, what's 3 minus 1? 2. What's negative 2 to the second power?
4.
And 4 times 3?
12.
Perfect. Let's check it with 2. So we've got 2 minus 1? 1. What's negative 2 to the first? Negative 2 times 3? Negative 6. Perfect. Yeah, that works. So that's how you find a formula, an explicit formula, for a geometric sequence. So it makes finding explicit ones for geometric and arithmetic pretty straightforward. All right, any questions on that? Okay. So that is 11.1. So that is the homework. Okay, notice most of that is just odds except 14. So everything is odd except number 14. All right, and you've got just about 20 minutes or so left. So please use the time to try to get some of that done. If you have any questions, or if you finish it, you could show me. I don't know if you'll finish it, but if you do have any questions on it, I can help you out. Yes, sir.